Hello. So now I'll be solving the Leecode question 1448. Count the good nodes in the binary tree. So what is a good node? A good node is basically if in the path from the root to the x there are no nodes with a value greater than x. Then we can call that node x as a good node. Let's see an example here. So in this tree we have there are a couple of there are several nodes actually. So so this is the root node, right? This 3 is the root node. Starting from 3, if you traverse to the left, so this 1, let's say this 1 is node x. So in between the node x and the root, there are no nodes, there's the node itself. So the node is definitely less than that of the root, right? And the definition for a good node is that the root x, there are no nodes with a value greater than x. So we can say the value 3 is already greater than the current node 1, right? So that means that's the reason this is not the, we can say, good node. So moving to the next node, that is 3 node. So this value we can see in between there is node 1 which is lesser, it's not greater or equal, right? And then next node is 3, so it's definitely equal. So that's the reason we can say this node is a good node. There are no nodes in between the root and the node that are greater than the node x. Same applies for 4. So there are no nodes greater than 4 in between. For 1, definitely the node 4 is greater than 1, right? Sorry, greater than 1, right? So that's the reason this is a bad node or not a good node, we can say. And this definitely for 5, and in between 3 there is node 4 which is lesser. That means there are no nodes greater than, we can say, 5. That's the reason this is also a good node. So for solving this, how we can do? So definitely we have to go level to level wise. Like first we have to consider 3, then we have to go to its child node as 1, then we have to go to its another child, that is 3. But if you see, while going to the next node, we should know what if, like, we should know if there is any node which will be greater than 3, right? Or we can say we should know what is the max node out of all the previous node from the root. Like, is there a node that is greater than 3? So we have to store that node, right? We can't just traverse it directly. Like, let's say for 3, the greater node is 3. When we come to 1, the greater node is 3. That's the reason that fails. For 3, the greater node is 3, and 3 is equal to 3. That's the reason it's a good node. Once it reaches 4, the greatest node until this point is 4. And here also it's 4. That's the reason 4 is greater than 1. That's why it fails. Right? Here also 3 is greater. And when it reaches here, the greatest node will be 5. So 4 is obviously less than 5, and that's the reason um, the 5 is also a greater node. So we also have to pass the, we can say, the previous max node. So we can say until root is by default a good node, right? Because there is no previous node to the root. So root is by default a good node. So we can say if you want to compute total number of nodes, well, let's say if we are doing a recursion problem, we are doing a DFS, the first search, let's say. So so we have to compute the root node. Then we have to check if, how many total nodes are there in the left subtree and how many total nodes are there in the right subtree, and we have to add it with the root node that are available. So it will be something like the root number of nodes at the root, and let's say root is a good node, okay, and then the number of nodes, good node in the left subtree, and the number of good nodes in the right subtree. Okay, so But while doing so, we have to maintain the max node as well. So let's start a basic code structure. Okay, so obviously we are doing a recursion, so let's define another function for our DFS. Okay, and inside the DFS we'll be passing obviously the node and the maximum value until that node. So let's say int max value, something like that. And okay, and initially we'll also obviously we'll calling the DFS function and passing the root, and by default we can pass the root value as the max function, because until this point that the max value is obviously the value at the root node. So the default function will be obviously we will check if that node is not equal to null, right? Sorry, if it's equal to null. If it's equal to null, obviously we have to return uh, 0, because here we will just return the max, sorry, not the max, but the total number of good nodes that are available at that point, right? So, so now, yeah, so we have the node and we have the max value until that. That's this node. Let's say 3 node. That is obviously not equal to null. That means we can proceed for checking the further stages. So if let's say if the node's value, okay, that is 3, is we can say less than or equal, okay, to the max value, okay. Let's consider for node 1. Okay, at node 1 obviously the max value will be 3, right, at that point. So node value is less, right? So actually we have to consider for the, sorry, we have to consider for the greater value. So if node value is greater or equal than the max value, like let's say for element 4, right? So node value is greater than the max value, right? So what we have to do is obviously the max value will become the node value, because it's the max value, right? The node value is now the max next max value. And next we also have to traverse the so we have to maintain a counter for the uh, total number of, we can say, uh, good nodes, right? So let's define a variable int res. By default, there will be uh, let's keep it as 0 nodes, right? And yeah, so let's now traverse the uh, inside of the loop, right? So we can say res will be equal to res plus the total number of nodes in the left subtree. So that is node dot left, and we can pass the max value at that point. We can do this same, sorry, and we can do this same step for the right subtree as well. Okay, and right, and here obviously we have at the end we have to return the result value. Like it will give how many total number of nodes, we can say good nodes are there at that particular point, right? And so here if that node value is greater, okay, like let's say the 4 is obviously greater than 3, right? That is the max value until that node. That means the next to max value will be 4, right? And also we have a good node, right? This is the good node, so we have to increase the value of res as well. So we can say res equal to 1, right? And that res will be, let's say, 1 plus the DFS from the left hand side, right? And then res equal to res plus this, that is the right subtree and left subtree. So we are actually implementing this formula right over here. And if there is no bad node, obviously the res value will be 0. So we will not be counting any good node at that point. Let's run this and check for any syntactical error. Okay, so it's working properly. Let's let's check for other test cases as well. Okay, so it's working properly, right?